In this video, we are going to be talking about nucleophilic substitution reaction in halogen compounds. So, for the ones who are from grade 12, this is there in your chapter Haloalkanes and Haloarenes. And the thing is, for this, that is nucleophilic substitution reaction, you have a lot of concepts that you have to cover. So, to make sure it's easier to understand, we're going to go from the basics. So substitution reaction basically means one group is going to get replaced, or one atom is getting replaced by an other atom or group of atoms. So nucleophilic substitution basically means a nucleophile is involved. So what is a nucleophile? A nucleophile is a group which is nucleus loving, which means it is electron rich. So it is an electron rich group, and the substitution reactions which are initiated by a nucleophile are called as nucleophilic substitution reactions. So here you have a nucleophile. We are going to denote it as Nu minus. It's reacting with an alkyl halide. So the C is the carbon atom and X is going to be a halogen atom. Now, due to the electronegativity differences between the carbon and the halogen, you have a partial negative charge on the halogen and a partial positive charge on the carbon. So nucleophile is nucleus loving and electron rich, which means it will come and attack this carbon atom. And what will happen? This bond will break, the X will get kicked out, and you get another compound, or rather you have the nucleophile replaced by the halogen atom. So that's about it. So here this is the nucleophilic substitution reaction. You have a nucleophile attacking the halogen molecule, the halogen compound, that is alkyl halide in this case, and this is leading to the replacement of the halogen with the nucleophile. Now in your textbook you have various examples of nucleophiles, and out of all of that, notice two nucleophiles. One is the CN and the other is the NO2. Now the CN is CN minus, okay, and it can also exist as you have it existing as this, or it can also exist as Cn minus. So the carbon can attack from the carbon side as a nucleophile, or it can attack from the nitrogen at the as the nucleophile. Okay, and such nucleophiles are called as ambident nucleophiles. So ambident nucleophiles have two ways by which they can attach at the compound. Okay, so if it was the carbon which attached, you'd get a cyanide, and if it was the nitrogen, it would be an isocyanide getting attached at the carbon atom which previously had the halogen. Next is the NO2. Now NO2 is O, N, double bond O, and this oxygen has a minus charge. Now either the nitrogen atom can form a bond or the oxygen atom. So if the nitrogen atom acts as the nucleophilic center, you will get a nitroalkane. So it'll attach as NO2. Whereas if the oxygen attached, you will get an alkyl nitrile. So these two nucleophiles are the ones, I'll just write, it will attach as ONO2. So the oxygen is the one getting attached to the carbon atom. So these two nucleophiles can act as ambident, are acting as ambident because you have two positions or two atoms to which the carbon atom can get attached to. So that is all about the nucleophilic substitution reaction in brief. Now we will be talking about the nucleophilic substitution reaction for the halogen compounds. So basically you always, whenever we talk about nucleophilic substitution reactions, the first thing we remember is the SN1 and the SN2 mechanism. So both these mechanisms occur with respect to the bulk or rather the presence of bulky groups and the absence of the same. So let's first start with the SN2 mechanism. So the SN2 mechanism is also called as nucleophile. It's a bimolecular substitution reaction. So what happens over here is, let me just put it here, OH minus is the nucleophile, okay, and then you have a carbon atom. It's bound to a chlorine, right, and you have a thick line, dotted line and a straight line, and these are all going to be the hydrogen atoms. Okay, so in this is actually called this is a wedge, solid line and wedge structure. So the dotted line shows that the hydrogen is behind the plane, okay, and this hydrogen is towards us because it's having a thick line, and these two are on the plane of the paper. So this is behind it, this is coming towards us, right, this is going away from us. So this is an alkyl halide, okay. Now the OH is going to come in and attack, and this is leading to the formation of this unique state. So here, let me just draw the structure first and then we'll talk. So you have an Cl, sorry, and you have a dotted line, you will have a thick line and a hydrogen, and this in turn will lead to the formation of OH, C, H, H and H. Okay, so let me just write it here. So dotted away, and this is going to be towards. So this is the basic representation. Now over here, OH minus is the nucleophile, okay, and this is attacking the alkyl halide, and this particular state is formed and you get the product, the alcohol. So an alkyl halide is getting converted to an alcohol. That is the basic reaction that we're observing here. Now let's talk about each and everything that this reaction has. First of all, the rate of this reaction depends upon the OH minus and the alkyl halide. It depends upon both of these. So it is a second order reaction. So it is a second order reaction because the rate of the reaction depends upon the nucleophile as well as the alkyl halide. It depends upon both of these things, and it's a second order reaction. Now in this mechanism you have the OH minus is going to attack. So assume this is the carbon Cl bond. So what is happening is the OH is attacking from the back. It is attacking at the back, and this is leading to the formation of something called a transition state. So a transition state is a condition where you have the carbon bound to not 4 but 5 atoms, and or in this case OH is a group, but it's having 5 bonds. Okay, so transition state is highly unstable. So I'm just going to write TS, highly unstable. Okay, and it shows the simultaneous formation of the COH bond and this breakage of the CCl bond. So the COH bond is forming and the CCl bond is breaking at a simultaneous process. Okay, and because the transition state is highly unstable, you can't really isolate and basically study it. So this is actually just one step. Okay, now notice that the reaction, the OH is attacking from the back. Okay, now this has led to something called as an inversion of configuration. So inversion of configuration has happened over here. First of all, let's understand what the word configuration means. Configuration, now we know that when we write a CH4, so this is the CH4 molecule, which means it's a methane. Now we know that CH4, the carbon and the hydrogen, all of these atoms are not going to get arranged like this. This is not its arrangement in a three-dimensional space. So they don't they don't get arranged like this, but instead they're going to be in a tetrahedral geometry. That's what we studied, right, last year. So the study of various atoms of, in a molecule in three-dimensional space, or rather not the study, but the study is going to be stereochemistry, but configuration is the three-dimensional, the spatial arrangement of a functional group. That's a configuration. So here what is happening is, because it is attacked from the back, this is getting removed. So you have an inversion of configuration taking place, giving rise to this product. If you see the hydrogen atoms, here you had it thick and here you had dotted line, but here it's the other way around. So there has been an inversion of the configuration. Next, what else did we have to talk about? Yes, so as we know, there's a simultaneous formation and breakage of bonds, and that's why you have the inversion of configuration taking place. Now, during this reaction, one more thing, you have, when the simultaneous bonds are formed, what happens is the carbon-hydrogen bond starts to lengthen. And what happens? The CH3, the hydrogen atoms, the bonds with the hydrogen atoms starts to get longer, and they tend to be on to the plane of paper. And that's about the transition state. And then next let's study about the reactivity. So you have three types of halogen compounds. You have a methyl. So let's assume this is a methyl, right? So this is going to be methyl. Then you have a primary. I'm assuming chlorine for all the cases. Okay. And then you have secondary. And then you have tertiary. Alkyl halides. So what you can see over here, now compare the methyl with the others. So in methyl we just have three hydrogen atoms. In ethyl, in primary you have a CH3. If you want, let's just expand the structure also. So you have a hydrogen. Okay, and I'll write this as an expanded form. So this also you have a three hydrogen atoms. Okay, now which of these do you think will undergo SN1, SN2 mechanism very easily? Now remember, for you to understand that, you need to remember the fact that the OH minus, the nucleophile, is attacking from the back. So when you have it empty, like in the methyl case, you have no issues. The OH minus can easily come and attack. So it can undergo the SN2 mechanism. Let's look at this case. This also, it's quite easy. It can undergo the SN2 mechanism. In case of secondary, it might be a little difficult, but it still can. But in case of tertiary, you have the hydrogen groups and the carbon atoms which will block the path of the SN2 mechanism, for the SN2 process to take place. And so the order of the reactivity for an SN2 mechanism is going to be methyl is more reactive than primary, than secondary, than tertiary. Okay, so for SN2 we started with the basic reaction, okay, where you have the formation of the, or rather the replacement of the chlorine with the OH minus or the OH group, and so you're getting an alcohol. So it's a second order reaction, and the rate of the reaction depends upon both the nucleophile as well as the alkyl halide. There is a formation of something called the transition state, which is highly unstable in nature, and because you have the simultaneous, and the reason it is unstable is because of the fact that carbon over here has 5 bonds, and this particular transition states show the simultaneous breakage of the CCl bond and the simultaneous formation of the COH bond. And in this, during this reaction, the inversion of configuration takes place. Now remember these words, inversion of configuration. We will talk about that in the next part of the video. Next, for tertiary, it's quite obvious that cannot undergo the SN2 mechanism. So there has to be some way it undergoes the nucleophilic substitution reaction, right? And that is going to be through the process of an SN1 mechanism. So unlike SN2, SN1 is actually a two-step reaction. Let's consider the 2-bromo-2-methyl propane. So that's going to be CH3 thrice. Okay, you know what? I'm just going to expand the structure and write it in the first step itself. So you have CH3 and Br. Now this is undergoing a nucleophilic substitution reaction with an OH minus, and this is leading to the formation, or rather the replacement of the bromine with the OH minus or OH. So you get a tertiary alcohol. Now, unlike in our and Br minus, if I'm not wrong, right? So unlike our previous case where you had the transition state forming in between, this reaction occurs as 2 steps. The first step is going to be the formation of carbocation, and this is because now we know that the CBr bond is actually quite polar in nature. This is due to the electronegativity of the bromine compared to carbon, and so it itself is polar, and so that will help progress the reaction. So first step, what happens is the C and Br bond is going to break for us to get a carbocation. So here you will have a positive charge because it's a carbocation. Oh, I'm sorry. This is the reactant. I am so sorry. So you have CCH3, CH3, Br and CH3. Now this is going to undergo a reaction where the CBr bond is going to break, and this is a reversible as well as a slow step. Remember, it's a slow step, and what happens? The CBr bond is going to break to give us a carbocation. Now next you have the incoming nucleophile coming. Okay, so the step 2 is going to be the attack by the incoming nucleophile on the carbocation. And this is actually a fast step, and this is giving us the alcohol. So there are 2 steps in this reaction. Okay, and here step 1, you have the formation of a carbocation. In the second step, the nucleophile is reacting with the carbocation, and this step is actually a fast step to give us an alcohol. Now in this case, the slow step is always the rate determining step. I know you haven't learned chemical kinetics till now because it has not been included in the portion for term 1 for the year 2020-2021. 2021 and 2022. But for a chemical reaction, slow step is considered the rate determining step. Rate determining step, as in that is what is going to decide as to how fast or slow the rate of the reaction is calculated based on the rate determining step. So the slow step, only the alkyl halide is undergoing a reaction. The nucleophile does not come in, and that is why this is actually a first order reaction. The rate of the reaction is dependent just on the alkyl halide, and that's why you call the SN2 as bimolecular nucleophilic substitution and SN1 unimolecular nucleophilic substitution reaction. So the rate of the reaction does not depend upon the OH minus, but it just depends upon the alkyl halide. So it's a first order reaction. Okay, now the rate, as we talk, so similar to this case, we have to talk about the intermediate, that is a carbocation. A carbocation is a carbon having a positive charge. So I don't know if you remember what you learned about carbocations in the previous year, but let me just recap it. So you have a CH. So this is going to be a primary carbocation. This is going to be a secondary carbocation. And this is going to be a tertiary carbocation. Now you have three types: primary, secondary, tertiary. Now alkyl groups are electron releasing in nature. Okay, in the previous case it was the bulkiness of the group that decided if a particular group is going to, if the primary, secondary, that was decided based on the bulkiness. But in this case we are going to be talking about the stability of the intermediate, and the intermediate over here is the carbocation. So a primary carbocation is bound to just one alkyl group, okay, whereas secondary is to 2 and tertiary is to 3 alkyl groups. Alkyl groups are electron releasing in nature. So because they are electron releasing, they will tend to stabilize this positive charge. So because there are 3 CH3 groups, they are going to stabilize the positive charge on the carbon atom. So the stability of the tertiary carbocation is higher than that of secondary, and that is again higher than that of primary. And because of this variation in terms of stability of the carbocation, tertiary alkyl halides undergo the SN1 mechanism more than secondary, that in turn more than primary. So that is about SN1 and SN2 mechanisms. So here you have this is the second order, and you have a transition state, and this is undergoing as a single step. But here in this case you would have it as 2 steps. First step is the formation of the carbocation because of the breakage of the CBr bond, which is highly polar in nature. Now or rather it's polar in nature, I shouldn't be using the word highly polar, but because of the electronegativities it's polar in nature. And the second step is going to be the incoming nucleophile attacking the carbocation. The decision as to which alkyl halide is going to undergo a SN1 reaction is dependent upon the stability of the carbocation formed. Tertiary carbocation is more stable than secondary, which is more stable than primary, and because of that tertiary alkyl halides will undergo SN1 mechanism. Now for a same alkyl group, the reactivity of the halogen compounds would be Ri is going to be more reactive than RBr, then RCl, then RF. So with that we're done with the basic understanding of SN1 and SN2 mechanisms. Now when we have allylic and benzylic halides, I'm just going to erase this part of it. So when we have allylic and benzylic halides, the carbocation formed during the SN1 mechanism are going to get stabilized by resonance. Now let's assume you have a CH2 double bond CH2, this formed a carbocation, okay, and you have a hydrogen atom here. Now what will happen is this double bond is going to get shifted here, and this is going to give us a resonance structure, and that is going to stabilize the carbocation which is getting formed. Another example could be our benzylic carbocation. So CH2 plus, right? So sorry, I should have done the double bonds because it's a resonance structure. I'm assuming you know what resonance structures are. So this bond is going to shift here, right? And we will not show the movement of positive charge because that is just wrong. And yeah, so here you have a positive charge, and this bond is going to shift here. So you will get another resonance structure, and CH2 single bond, and then here the positive charge, then this bond shifts downwards, and so here you have a double bond, and a double bond CH2, positive charge, and this comes back into the ring to give us the benzylic carbocation. So in case of allylic and benzylic carbocations, they are going to be resonance stabilized. So with that, we're done with the basic SN1 and SN2. Next, we will start studying about something called as optical activity, configuration. I'll just talk about that. Let us discuss the stereochemical aspect of nucleophilic substitution reactions. Now, when we spoke about SN2, I said that there'd be an inversion of a configuration. So the whole concept of inversion of configuration can only be understood if we have a basic idea as to what stereochemistry actually is. So stereochemistry is the study of the molecules in a three-dimensional space. So the plane of paper is a two-dimensional space, but the stereochemistry is going to be a 3D study basically. So under that, you have various concepts that you need to know about. Let's begin with the first one, that is optical activity. So optical activity is basically, first of all, you have something called as a plane polarized light. So this is a plane polarized light. Generally, light can be in any direction. Okay, it can usually, you have it like this, can be in any direction, but the plane polarized light will have the light only in it is polarized, which means it's going to be only in this direction, and this is because the light is passed through something called a Nicol prism. So organic molecules, when they are put in the, suppose this is the organic molecule in this box and it is interacting with the plane polarized light, what happens is they tend to rotate the plane polarized light. So they will rotate the plane of the plane polarized light. So based on that, the organic compounds are classified as two: dextrorotatory and levorotatory. So dextrorotatory means the organic compound rotated the plane of the plane polarized light to the right, whereas levo is going to be to the left. Okay, and dextro is denoted as D or plus, whereas levo is denoted as L. It's supposed to be small. Capital is for the configuration, but this is the rotation at the plane polarized light. So D and positive, or L and negative. So this is also referred to as D form, and the levorotatory is referred to as the L form. So we cannot predict which direction the optically active compound will rotate the light to, because this is done through an instrument called the polarimeter. So polarimeter will decide, or will be able to observe and tell us if an optically active compound is rotating the plane of the plane polarized light to the right or the left. So that is optical activity. The next thing we're learning about is something called as molecular asymmetry. So it was actually Louis Pasteur who observed that there are certain compounds. He found that there are certain compounds which were forming mirror images. So what he saw was that they were able to rotate the plane of the plane polarized light to the right, and the opposite, the mirror image, was able to rotate to the left. So he noticed that what he did was he took these crystals and dissolved them in an aqueous solution, and to form an aqueous solution, and it showed that the opposite mirror images were able to rotate the plane of the plane polarized light to the opposite direction, but to equal extent. So the difference in direction was actually, he assumed that it was because of the three-dimensional arrangement, and that is where we have the beginning of an entire branch of chemistry called stereochemistry. So according to two scientists, the Van Hoff and C. Bell, in the same year, they said two things. First of all, the spatial arrangement in a carbon compound, around a carbon, is going to be tetrahedral. That was the first thing they said. The second thing, the substituents, so in our carbon, in our molecule, we have, let's take this carbon atom, it is bound to 4 different substituents. So A, B, C, D, 4 different substituents. So this carbon is referred to as asymmetric carbon, or it is also referred to as a stereo center. So this carbon has the substituents arranged in a tetrahedral geometry, and it is bound to 4 different substituents. Then it is called an asymmetric carbon, or it's also called a stereo center. So this asymmetric carbon is able to show the optical, due to this it is able to show optical activity. Now the asymmetric carbon alone does not, but you also have the non-superimposability of the mirror image that leads to the optical activity of a compound. So that is molecular asymmetry. Next, we'll again go back to optical activity. Now, when I told you, okay, an optically active compound is able to rotate it to the right, or rotate the plane polarized light to the right or left. So an optically active compound is also called as a chiral compound, and this phenomenon is chirality. So an optically active compound is also referred to as a chiral compound, and they have whichever has a superimposable mirror image is considered to be achiral, and it will be optically inactive, and it will not have a asymmetric carbon. So the carbon atom, if it's not bound to 4 different groups, and if it has superimposable mirror images, then it's going to be optically inactive and achiral. Whereas so for us to figure out if a compound is going to be optically active or not, to what extent it's going to figure out is by the polarimeter. That will only measure the angle, okay, and that can only tell us if it is going to be D or L. We cannot predict it on a piece of paper. Okay, this compound has this arrangement, and so this should be a D isomer or an L. But it's actually through a polarimeter that we can say that, okay, it's going to rotate it to the right or left. But based on we can draw it on a piece of paper, or we can generate the molecular models using the ball and stick model, and we can figure out if a compound is going to be chiral or not. We can say that, okay, it's going to be optically active or inactive. But to what extent, we'll not know. But it can be optically active or inactive, can be figured out based on the presence of the asymmetric carbon and this non-superimposable mirror image. Now let's take the example of propane 2-ol. So propane 2-ol is CH3, CH2, CHOH. 1, 2, 3, oh, CH2OH. Now, we'll only be talking about this carbon atom. Okay, these two we're not talking about, we're talking about this carbon. So, here you have a carbon, right? And you have a hydrogen atom and you have the OH. These are both on the plane. Whereas this is going to be, this CH3 is behind, sorry, sorry, I am so sorry. 2-propanol, right? So we're taking the second carbon atom. I'm so sorry. So, and you have a CH3 here. And you will have a CH3 behind the plane of paper. Let's assume this is the first structure. This is propane 2-ol. Alright. Now, when we talk about its mirror image, okay, we'll be taking its mirror image, which means it will be like this. So this is like this. It'll be its mirror image, right? So you're basically flipping the sides, and so you have a CH3 here, you have the hydrogen still on the plane of paper, and then you have another CH3. Now, when we rotate this structure, we are rotating this structure, what we see is that the structure is actually superimposable on the first one. So what we are getting is, when we rotate it, it's basically going to be similar, or rather same as the first structure that we have over here. So this means that this compound, this carbon, is not going to be optically active because these are superimposable and this is not going to be chiral in nature. There is also one more thing, we didn't have to rotate all of that. It is quite obvious from this carbon atom. Okay, it is bound to one hydrogen, good, but the CH3 groups, there are two CH3 groups, which obviously makes it not an asymmetric carbon. Okay, and the reason it's called an asymmetric carbon is because it does not have any symmetry. So because these mirror images are actually superimposable, this compound is not going to be optically active. Now let's take an example of an optically active compound. Here we are taking butane 2-ol. So butane 2-ol is CH3, CH2, CH3, OH. Now this can be written as C2H5, right? And this is a CH3. So the first structure is going to be OH, and you have the hydrogen at the bottom, and you have a thick line denotation of C2H5 and a dotted line of CH3. Okay, now when you have its mirror image, you have OH, I'm sorry, it should have been the other way around, HC, okay, and you have the thick line of C2H5, down H, and at the top you have CH3. Now again, in the previous case, we'll be rotating this by 180. So when we rotate it by 180 degrees, what happens is these two tend to flip. Okay, so this is going to go back and this is going to come forward. So despite looking quite similar to the first structure, this structure is actually a non-superimposable mirror image. So the ethyl group is going at the back and the methyl is coming forward, whereas in this case it was methyl which was forward and ethyl at the back, which means these are non-superimposable mirror images, making it chiral. And one more thing, it has the carbon atom has 4 different substituents. So if you're very, if you're confused to see, okay, you don't understand how to figure out if it's going to be superimposable or not superimposable, the first thing you can check is if a particular carbon atom has 4 different substituents or not. That can easily, make sense. If it'll help you understand if a particular compound is going to be chiral or achiral. Now, there are other examples of chiral molecules, examples like 2-chlorobutane, 2,3-dihydroxy, propanal. All of these are chiral compounds. Now, there's something called as enantiomers. So, enantiomers are compounds, obviously. They're like isomers, okay? And where the stereoisomers, which are non-superimposable mirror images, are enantiomers. An example of that is this and this. These two are enantiomers. These are non-superimposable mirror images, okay? And these two are also enantiomers. So they are non-superimposable mirror images. Okay, now when we talk about enantiomers, we also need to talk about something called as a racemic mixture. Now, as I told you, our optical activity. When a molecule is showing optical activity, it can rotate the plane of the plane polarized light to the right or the left. Now, a racemic mixture is a mixture of a compound, okay, which has both the isomers in such as both the stereoisomers in equal quantity. So, it will have suppose 10 molecules of D and 10 molecules of L, and because of that the net rotation, the net optical activity of that mixture becomes 0, and that kind of a mixture is called a racemic mixture. So this is represented as DL or plus minus. It consists of equal amounts of both the D, the dextrorotatory, as well as the levorotatory, and that in turn leads to a total optical activity of being 0. So this mixture will not show any optical activity because the D will rotate it to the right, the L will rotate it to the left, and because of that they will cancel each other out, leading to no optical activity which is observed in a racemic mixture. And this process of conversion of an enantiomer to a racemic mixture is called as a racemization. The next term we are learning about is retention of configuration. Okay, TIOM. So retention of configuration means that during a chemical reaction or during the course of a chemical reaction, the configuration of the stereocenter is going to stay the same. Notice I'm only talking about configuration. It necessarily does not mean that the optical activity of the product will be the same as that of the reactant. It can be same or different, but the configuration of the stereocenter is retained. Generally, this is observed when the reaction does not take place at the stereocenter. So let's take the example of the reaction of 2-methylbutane 1-ol. So 2-methylbutane 1-ol, we have a stereocenter at the second carbon atom. So this carbon atom has, it has a dotted line, which means the CH3 group is behind the plane, whereas these two wedges show that the hydrogen as well as the CH2OH are going to be towards us. So CH2, CH3. Now, when this compound is undergoing a nucleophilic substitution reaction with HCl, what is going to happen? This bond is going to break, and this is the stereocenter, so the reaction is not taking place over here. So the product will be a CH2Cl, and you have a hydrogen atom CH3, then at the bottom you have a CH2 and a CH3. Now this compound is 2-methyl butane 1-ol. Okay, whereas this compound is 1-chloro 2-methyl butane. So here this compound is also has one more important sign, that is a plus sign in front of, sorry, a minus sign in front of it. The minus sign denotes that this is actually a levorotatory compound, and the product is going to have a plus sign. Because of its optical activity, based on its optical activity, it was observed that the rotation was towards the right. Whereas this compound, it showed that it was to the left. So levorotatory compound has converted to a dextrorotatory compound. But the reactant and product. So, but then the carbon, the stereo center, this carbon atom, it has the same configuration in both cases. So there has not been a change in the configuration, there just has been a change in the optical activity. So when a chemical reaction takes place, three things can happen. Let's assume that this compound is undergoing a reaction. So you have a CH3 and an X, and you have a C2H5. So we are assuming this compound is undergoing a reaction. It's an alkyl halide. Okay, there are three things that can happen. Okay, so since the reaction has to take place at the stereo center, it's obvious there will be a change in configuration. Retention occurs when the reaction takes place at a usually occurs when the reaction takes place at a particular another carbon which is not the stereo center. But in this case, you have the reaction taking place at the stereo center. We are assuming X is going to get replaced by Y. So the first thing that first possibility is you have the retention of the configuration. So that means that C2H5, you'll have C2H5 and Y on the plane of paper, and you have the CH3 and the hydrogen, CH3 towards and hydrogen away from us. So let's assume this is compound A. Another possibility when Y attacks is carbon, and there is going to be a flip. So you will have a Y atom here, and then you will have a CH3 and a hydrogen. So it's forming a mirror image. There is an inversion of configuration. We notice that when it forms B, there is an inversion of configuration, and that is what we said will happen in case of our SN2 mechanism. And the third possibility is we get equal amounts of A and B. So this will be optically inactive because it's a racemic mixture. The rotation shown by A would basically be, or rather, I'm sorry, I shouldn't be calling it a racemic mixture. I am so sorry. This A plus B is a mixture of the retention as well as an inversion product in equal amounts. And it forms a racemic mixture. So let's look back at the stereochemistry of the SN1 and the SN2 mechanisms. So let's begin with SN2. It's a single step reaction, as we know. So for SN2, okay, let's take the compound CBr, okay, and at the bottom you have C6H13. It's a long compound, and a hydrogen atom away from us, and a CH3 group which is on the plane of paper. Now we are assuming a nucleophile OH minus is coming and attacking. So what happens here? So in an SN2 mechanism, the OH has to attack from the back. right? And that leads to the formation of a transition structure. Now when it attacks from the back, this bromine will start to come out. So there will be an inversion of configuration. And so this is pulling it away, and OH is going to come and get attached. So there will be an inversion of configuration. So you'll have an OH over here in the carbon. Then you have the CH3 and H and C6H13. So here plus Br minus. So this is happening because there is a simultaneous formation of a new bond from the back and a simultaneous removal of the bromine. So it will pull. When it pulls away, there is an inversion of configuration observed. So there is an inversion. So this is, in this case, in SN2, we know that the OH will not attack from here or from here. It is attacking from the back, and because of that there is an inversion of configuration. But in SN1, the story is completely different. We know the reaction has to take place as two steps. So the first step would be the formation of a carbocation. So let's take this compound, and we are assuming it is reacting with, it's reacting as an it's following the SN1 mechanism, and you have a bromine atom over here and you have a CH3. So this is an asymmetric carbon because it has 4 different groups attached to it. Now the first step is going to be the slow step. So the slow step is going to lead to the formation of the carbocation. So CH3, this hydrogen, and a CH2, CH3, and this carbon has a positive charge plus bromine negative charge. Now in the previous case we knew that the OH has to come attack from the back, and so the reaction will proceed through the formation of a transition state. But in this case we don't have that particular issue because the carbocation which is formed, the incoming nucleophile, the OH minus, can attack from this side or from this side as well. So let me draw those structures. Okay, I'll just erase this and draw it here. So the carbon has, this is the carbocation, right? And it has 3 groups attached to it. So CH3, a C2H5, and a hydrogen atom. So this in your textbook is denoted as a triangle, right? Now what happens is the OH minus can come and approach from this side, or it can come approach from there. So there are 2 possibilities of formation of the product. So in the first case, case 1, it can attack from, when it attacks from this side, the product formed is going to be CH3, H, and a CH2, CH3, and a OH. Okay, but when it attacks from this side, that is from the back again, it will give us OH, CH3, sorry, H, and a, that looks like an I, I'm sorry again, H, and a CH2, CH3. So what is happening is the OH is either can attack from this side or it can attack from this side. When it attacks from this side, there is an retention of the configuration. Oh, you can't even see it, I'm so sorry. And when there is an attack from this side, there is going to be an inversion of the configuration. So there is an inversion similar to that of observed at SN2 process. So with that, we're done with the stereochemical aspects of SN1 and SN2. For you to understand the stereochemical aspects, you need to understand the concepts of optical activity, which basically means that a compound is able to rotate the plane of a plane polarized light to the right or the left. If it is rotating to the right, it is a dextrorotatory compound. If it's rotating it to the left, it's a levorotatory compound. Configuration is the arrangement or the three-dimensional arrangement of a molecule. So it's the spatial arrangement, and the mechanisms, the various. So a compound which is optically active consists of a tetrahedral shape, and the carbon is tetrahedral and the carbon is asymmetric, which means it is bound to 4 different groups. It is optically active, but we do not know to what extent. Is it levorotatory, it's dextrorotatory, all of that is not known. It is only known that it's optically active and chiral in nature. So chiral compounds are also they have a different they have various substituents. The carbon atom has various substituents, and it has a non-superimposable mirror image. The ones which have a superimposable mirror image are considered achiral because they'll be optically inactive. Now, optical activity is measured based on the angle to which the plane of the plane polarized light is rotated to, and that is done so by using a device called a polarimeter. We then moved on to study about enantiomers, which are basically non-superimposable mirror image. C and D are enantiomers because they are non-superimposable, but they are mirror images. A racemic mixture consists of equal amount of D as well as the L isomer. So the D isomer will rotate the light to the right, and the L will rotate it to the left, and it is denoted, and because of that they will cancel each other out, and so the optical activity of that particular mixture is going to be 0, and it's the racemic mixture is denoted as DL or plus minus. Now there will be reactions where there is a retention of configuration that occurs. So when the retention of configuration takes place, it's usually when the reaction is not at the stereo center. So this carbon atom has not undergone a reaction, it's only this one that has undergone. But despite the fact that the configuration stayed the same in both these cases, the optical activity actually flipped. It went from being a levorotatory compound to a dextrorotatory compound. So in a chemical reaction, there are 3 possibilities. It can be a retention product formed, an inversion product can be formed, or there can be a mixture of both an inversion as well as a retention product. From there, we moved on to understand the SN1 and the SN2 processes. In SN2, because of the fact that it's a single step process, what is happening is the OH minus is attacking from the back, and what the Br is going to get pulled, and there is going to be an inversion of configuration taking place. So the product which we get is going to have an inversion of the configuration. Whereas in case of an SN1 reaction, you have the formation of a carbocation. This carbocation can get attacked either from this side or this side. So when the OH minus is attacking from the right, it is leading to a retention of configuration. So this is the retention product, whereas this is going to be the inversion product because the OH minus attacked from this side. So because it attacked from the back, similar to what we observe in SN2, you have the inversion of configuration. With that, we're done with the basic idea about nucleophilic substitution reaction for haloalkanes. And for you to understand it in much detail, this is the basic thing that you need to know for right now. With that, we're done with this topic. For the overview of the complete chapter, do check out the other videos, and the notes are given in the description below.